All right, let's get started. Good morning and good afternoon, everyone. And thank you so much for attending the Snowflake webinar on architecting modern data applications. My name is Megan Schoendorf, and I'm a senior software engineer at Snowflake on the applications team, and I'll be your presenter today. First, some housekeeping. I'm going to hold all questions until the end of the presentation, but please ask any and all questions throughout the duration of the webinar via the Q&A box on the right-hand side of the slides. At the end of the presentation, I'll go through as many as I can. I am expecting the content of the presentation to take about 20 minutes, and then we'll have 10 to 15 afterwards for doing questions. If you'd like to learn more about Snowflake, I'd encourage you to review the resource box we've included. There are a couple of links to the upcoming webinars, a new ebook content, and our popular virtual hands-on lab where you can try Snowflake for free in an instructor-led environment. Lastly, this webinar will be recorded, and we'll send you a link to the recording tomorrow. So again, my name is Megan Schoendorf, and I came to Snowflake recently by way of acquisition. I was the first hire and architect at a startup called Stride, a customer data platform for marketers. When we were just getting started a little over 3 years ago, I needed to choose an analytical database to power our product. I considered several solutions, and evaluating primarily on query performance and maintenance requirements, I landed on Snowflake. We spent the following 3 years using it to develop applications until this July, Snowflake acquired Stride and formed the applications team. Today, I want to talk to you about a couple of the lessons that I learned building on top of Snowflake and how we used it to help us achieve two of our architectural goals. The first is service-oriented architecture, and the second one is continuous integration and continuous delivery. For each of them, I'm going to cover what they are and why they're important, what's really hard about them, and how Snowflake helped us to get to these goals. And at the end, of course, we'll do the live Q&A. All right, so first topic is service-oriented architecture, or what I like to call just right services. A service-oriented architecture is a style of software design where your application is divided up into multiple services, each with a limited scope of responsibility. The size of these services can span a wide spectrum. On one end, you have the strict paradigm of microservices, in which everything has a very specific job and completely isolated state, and the services only talk to each other over the network. On the other end of the spectrum, you can have larger services. Maybe they own bigger chunks of business logic, or they have some shared state in a database or a queue. I tend to prefer something in the middle, what I like to call the just right service architecture. But regardless of the size that you go for, these services allow you to organize your architecture in much the same way you'd want to organize your code. Encapsulated units of logic in reusable components that are loosely coupled with one another. This loose coupling is the thing that's most important, and it's what allows you to do a lot of the really interesting things that you can do with Stella. The services get to be independent from each other. They get to be independently architected. You can choose different languages, different frameworks, different persisted state as needed. This is the idea of being able to choose the right tool for the right job. They can be independent, tested, and deployed. This is key to keeping your teams moving quickly. A blocker on one team's code shouldn't prevent another team from moving forward. At a previous job, I worked at a place where we did deploy on a monolith, and I can't tell you how many times I'd be ready to get my code out the door, only to find that day's deploy blocked because of a bug somewhere else. It was always really frustrating. And so, as you can imagine, it scaled poorly as the organization grew. And so I've sort of always been at a place that either is trying to go to a service-oriented architecture or is already at one. But the key takeaway here is that independently deployable services will prevent a single problem from grinding your entire organization to a halt. Finally, each service can be tuned and scaled independently. For example, you might have an authentication service that sees peak load during business hours. It can be scaled independently from a background job with relatively stable load. Conversely, a monolith would need to be over-provisioned in some areas in order to accommodate all the load and performance requirements of another. This means that you're going to be paying for resources that you aren't using, and that can be prohibitively expensive for even mediocre performance guarantees. All right, so service-oriented architecture sounds great. It has a lot of upsides, but it's also really hard to implement. The most frequent complaint that I've heard is about the overhead associated with the services. Each one needs to be monitored and maintained, tested, and scaled. And this gets even worse with service proliferation. Once you have a hammer, it's easy to see everything as a nail. And the next thing you know, you've got too many services that are too micro, and the cost of the overhead outweighs the benefits, especially if you haven't done the work to automate as many of those processes as possible. The next class of issues come from your database, and they tend to be even more challenging. A service-oriented architecture is, at its core, highly parallel, with many services running independently. Your database needs to support this level of parallelism through concurrent reads and writes and a sane locking policy. Of the products that we investigated, we saw that one of them had a hard organization-wide concurrency limit of 50, even if you were only doing read queries. That meant that you could scale up your services that were doing reads, and suddenly they're going to interact with each other by locking each other out because you'd hit this concurrency limit. There's another product that we looked at that would support hide read concurrency, but the inserts and updates took out a lock on the entire table that they touched. This meant that if your use case involved maybe multiple instances of a single service needing to write to the same table, those instances would lock each other out. Another use cases where one service writes to a table that another one needs to read from, again, they would be locking each other out. And this fundamentally hamstrings the parallelism that you're trying to get from using multiple instances of a single service. So suddenly services that were meant to be deployed and scaled independently would require really tight coordination in order not to have the database give you some troubles. The last thing that can be really challenging about service-oriented architecture is the fact that they're independently deployable means that you can wind up with version compatibility headaches. Not having to do the coordinated release is great right up until you need a coordinated release because you're trying to make a backwards incompatible change. That change can come to the interface, or it could come in the form of a schema change to some shared data. That usually results in something that has to be super painful, multi-phase, and requires coordinating across teams. It's never a good thing. All right, so let's talk about how Snowflake can help you to address some of these problems. So of all the databases that we evaluated, Snowflake was the best complement to a service-oriented architecture. The first thing that really stood out to us about it is its key differentiator, which is the separation of storage and compute. For those of you who aren't familiar with it, I'll just give a quick definition. There's a storage layer in Snowflake that elastically scales so that you don't have to migrate your data as it grows, and it's really cheap. Separately, the queries are executed in what's called a virtual warehouse. These warehouses come in different sizes. The larger ones are more expensive, but they also perform faster. And the way the billing works is that you get billed per second of usage. And so that means that if you take a single query that maybe takes 10 minutes to run on a small, but 5 minutes to run on a medium, it'll cost you twice as much per second, but that ends up coming out to the same total cost, which really means that you're given the freedom to choose the warehouses that make the most sense for whatever your workload. One of the benefits of SOA is the ability to choose the right tool for the job. And so with Snowflake, that meant that we could choose the correct size warehouse. If a monolith architecture can be described as one size fits all, Snowflake delivers the opposite, many sizes for many services, thanks to the separation of storage and compute. So another issue I was talking about was this idea of resource contention. So what if your use case involves one service writing to a table that another one reads from at the same time? In Snowflake, that's no problem because reads and inserts are non-blocking. So that means that you can be inserting to a table and reading it from the same time with as much concurrency as you want, and you're never going to run into a problem. There's also, of course, updates and deletes to think about. These operations only lock at the micropartition level. A micropartition is a block of data, and you get to control how your data is organized into these blocks so that you can basically pick what's called a cluster key, which effectively is kind of like a sort. And if you choose it correctly, then your updates won't ever end up writing to the same micropartitions. To just give you an example of that, at Stride, we tended to have processes running on a per client or a per tenant basis. And so our top level cluster key would be tenant ID. And this meant that we could have lots of different processes running updates, but they would never actually update the same micropartitions. So they never locked each other out. The other way that Snowflake supports parallelism is through a feature called multi-cluster compute. After you've chosen the size of the warehouse that you need for a service, you can also tell Snowflake that you want to auto-scale the number of warehouses in order to meet the demand. This is really helpful for services like the UI for a web app, because those services tend to see peak load during business hours. So you're not just going to choose 3 warehouses, for example, for all the time. And also, you're really, really sensitive to the 99th percentile performance. Like, no customer wants to pay the price of having their queries queued up. And you also don't want to have to build all the tooling yourself to have these things auto scale. So having Snowflake do the auto scale for you means that you're spending a lot less time building tooling yourself, and you're only paying for what you use, because things will go back to sleep when there's no demand for them. So this auto scaling was really great, and kind of got at this idea that I was talking about earlier, which is the overhead associated with having services. What you really want is to have the tools that you're leaning on give you all the help that they can, so that you're not spending your engineering efforts reinventing the wheel. Snowflake is a fully hosted and fully managed service, and so that's one less thing that you have to manage. They also have a couple of serverless features that we found really helpful. The first one is Snowpipe, which will automatically ingest data from, for example, S3 buckets as soon as it's available. So all you do is sort of configure it, point it in an S3 bucket, and then it'll just pull things into whatever staging table you told it to go to. And that's one service you don't have to manage. Let's say you have even more complicated ETL requirements. You aren't just doing inserts, for example, but you actually want to do sort of merges or updates. Maybe you have to do joins across different tables. For that, you can use something called tasks. These are just schedulable things that will run. They'll run on a frequency, and they can execute either JavaScript or SQL statements. And so they can do things that are quite complicated. And it's another service that you aren't having to host yourself. So that made a huge difference for us in the way that we managed getting our data into Snowflake with really very little effort from the engineers. Okay, so the next topic is continuous integration and continuous delivery. Deploy early and often and as automatically as possible. So CI/CD, I think it goes hand in hand with a service-oriented architecture because you don't want to have to manually deploy several services. So you can imagine that doesn't scale very well. And so the more services you have, the more important it is that you focus on making your deploys as low friction as possible. And leaning on sort of any automation that you can. What does CI/CD really actually look like today in a lot of organizations? So an engineer starts by checking out a branch, and they're going to develop locally. And when they're ready to go, they'll check that code in to be tested and reviewed. At this point, automation kicks in and runs a script that will hopefully compile the code, run a suite of tests, do static code analysis, and do the build. Meanwhile, the pull request is getting reviewed by peers. When all that's done, then the last required manual step happens, which is the merge into a master branch. At this point, the continuous deployment phase, where the code will automatically go to staging or canary environment, final tests and checks are run, and then you get deployed to prod. The degree to which you've achieved continuous deployment directly relates to how much happens in step 5 that cannot happen in step 2. So what I mean by that is, let's say you have an integration test that can only run after you've merged into the master branch. That means that even if that integration test is automated, it's still an expected outcome that it will fail because it hasn't run yet. And if you have test failures as an expected part of your CI/CD, that's going to block up your build and release pipeline, and that's going to add a lot of friction. It's going to add a lot of friction into your build and release. So having low friction, frequent deployments really relies on you having very little happen in step 5 that can't happen in step 2. The second thing that can really slow down these deployments is doing these backwards incompatible changes that I talked about earlier. This can include updates to a service's interface or changes to the schema of a shared database. This kind of deploy can be really challenging. It requires coordinated release between different teams and different services. Probably doing a data migration, it's going to be multi-phase, maybe you have to take downtime. No matter what you do to make it, to reduce your pain, it's still going to add a lot of friction into the system. So the fix, so all your tests need to happen before you merge to master so that master can always be green and deployable. And if that's the case, deploying to prod can actually be automatic. And you also have to greatly reduce the frequency of your backwards incompatible changes. And the databases that you choose should support and not hinder this effort. So there are two features of Snowflake that we relied on really heavily in our build and release. The first feature is called zero copy clones. And what this means is that when you make a copy of an object in Snowflake, such as a table or a database, the operation is only going to take a few seconds because none of the actual data is getting copied over. You do, of course, still have that. If you copy a database with data, you still have access to that data. But under the hood, it's happening extremely quickly. At Stride, the way that our unit test worked is that every suite would start by making a clone of an empty database that had our schema in it. And that meant that that suite of tests could be running in this completely isolated environment, and you could have as many of them running in parallel as you want. This, of course, meant that you could be running your unit tests before you had to merge into the master branch, which was super important. The next thing that we looked at was how we were going to do our integration tests and our regression tests. So the integration tests were really important for managing version compatibility, and of course, regression tests to make sure that you haven't introduced any regressions into your code. The biggest thing that we did here was that we had the starter database with a bunch of data in it, and we would make two clones of that starter database, and we would have both our old code and our new code run against these two databases, and we'd send them through our entire pipeline. And then out the other end, we would have sort of the resulting two databases that would show that you could run queries against to do a diff. And this would show us whether or not we had any regressions. That was really useful. Again, this was something that could always happen in a branch. It wasn't like you had to get it into the master branch to run against the single staging database that we had out there. And you always had the same starting point. And so it really also helped to reduce the noise associated with, false test failures. So 100% of our testing and reviewing was able to happen before any of our branches got merged to master. So this was a huge help to us in keeping our master branch green and deployable. Okay, and so then the last feature I'm going to talk about is this unstructured data feature. So for us, the last piece of the puzzle to really achieving this idea of CI/CD was in reducing the number of backwards incompatible changes we needed to make. Unstructured data is a really challenging thing to do in an OLAP database. We found that a lot of the other competitors that we looked at, if they had unstructured data at all, then you would take a performance hit for using it. It'd be way better to use the primitive column types. We had to have unstructured data anyway because we were hosting our customers' data and they couldn't tell us what the schema was ahead of time. So it was already a hard requirement, but the fact that we weren't taking a performance hit for using this column type called variant, which holds JSON data. The fact that we weren't taking a performance hit there meant that we could rely on it even more heavily and put critical things that we wanted to be querying our data by in there. And it gave us so much more flexibility in the way we designed our schema. I still really like using primitive column types for the columns that are, that are definitely going to be there. And it helps to make your schema a little bit more self-documenting. But every single table that we designed would get at least one variant column that could hold this unstructured data. And it acted as a catch-all for the part of the schema that we knew would be subject to change as our product developed. From here, we didn't really have to do schema changes because what we were doing was changing the schema of the JSON, which is a migration that you can do, for example, on read, and wouldn't require doing that painful multi-phase deploy that I was talking about earlier. This strategy allowed us to drop the number of these painful migrations by at least an order of magnitude, and it really kept us deploying on a quite a frequent cadence. So between these two features, robust testing framework and these rare data migrations, we were really deploying quite often, not quite continuously, but we got really close, and we were really, really proud of that. So that is it for the content of my presentation. Just in time, in about 20 minutes. I'm going to take a few minutes and read through some of the questions, and then I'll pick some to answer. And feel free to add more now if you've got any. All right, so I have this first question, came in from the company Happiest Minds. The question is, while ingesting data using Snowpipe, can we perform transformations other than simply doing a copy? So the answer to this question is no. So the Snowpipe is useful for doing the sort of the insert only version of your ETL. But the way that we tackled this is we would first run Snowpipe in order to get data in. In our case, we were doing the AWS cloud version of Snowflake. And so we put our data into S3, Snowpipe ingested it by doing inserts directly into these staging tables. And then we scheduled tasks that did the more complicated sort of joins and merges. And so these tasks would then move the data from the staging tables out into their final resting place. But that is a great question. Snowpipe is meant for doing inserts only. All right, let's see. So I see a question here from the company Filevine, which is, how does unstructured data get queried? This is a great question. Even after I'd been using Snowflake for a while, I'd find every time I was writing queries for unstructured data, I would pull up their documentation on it. They sort of have this one article that walks you through all the different ways that you can interact with unstructured data, but you can treat it just like a JSON object. So you can do, whatever the name of the column is that has it, open square bracket, name of the key, close square bracket, for example. And you can do as much nested JSON as you want. But there is a great article that we can link afterwards on how to query unstructured data that sort of has all the tips and tricks in there. Here's a question about what's the mechanism for deploying updates to Snowflake in a CI/CD context? Do you represent all your changes in SQL, and how do you store them in a version control system? This is a great question. This is something that I would love to see Snowflake publish a library around, but the way that we handled it at Stride is we wrote a little migration tool that we called Snowgrate for Snowflake migration. We were very proud of it. And what we did was we would have a folder with migrations, and every time you wanted to make a change, you'd make a new file that would represent, it would have SQL in it to represent that migration. And then our tool would execute by looking at a table in our database called applied files and seeing the difference between what was in this table and the files that were actually in the folder. And then we would execute any migrations that were new, and then, of course, write the names of those files to this applied files table. This meant that you could sort of point this tool and this set of migrations at any database, and it would always just apply sort of the new ones. And this also allowed us to do version control around our migrations. But that is a good question. I found that we looked around for sort of third-party SQL migration tools and really didn't find anything that we thought was really amazing. So we just wrote one ourselves. Here's a question. Did you deploy any real-time applications? And if so, what challenges did you face? So we did. We were a marketing platform, and we had both this need for sort of these heavy analytical databases where people were trying to segment their audiences according to their behaviors and actions they'd taken. But they also wanted the ability to trigger actions based on things that were happening close to real time. For this application, we needed two different databases, right? Obviously, we're using Snowflake to power the sort of heavier analytical type queries and like all the reporting that we showed to our customers about their marketing campaigns. But then we would use a transactional database to sort of be like the OLTP complement. And I would say the hardest thing that we faced was keeping these two databases in sync. We wrote something ourselves. I do know that there are good third parties out there and that there are also some good products coming down the line, but we had to come up with a way to get our data out of our transactional database and into an S3 bucket so that then we could have Snowpipe sort of pick up the data from there and keep our transactional database in sync with the Snowflake database as much as possible. We were able to do it on sort of a 5-minute delay, which was, I think, really good. Because people would, of course, want to see as quickly as possible in the UI like what was going on. But I do think that syncing between two different databases is always a challenge. It's always something that you want to be really thoughtful about. So actually, I'm going to take a question I don't know the answer to. From FileVine, we have how many columns are allowed in a database table. I'm sort of, I never hit a limit, and I don't know that there is a limit to the number of columns allowed. But I am very interested. I'll find documentation for that one, and we can send it out afterwards. But this isn't something. It isn't like sort of your standard Postgres table where you've got limits to the number of things, the width of each column, for example, because it's a columnar store. Here's a question, which is, does Snowflake require a DBA, database administrator? In my experience, we did not have a dedicated database administrator, and this was one of the things that caused us to choose Snowflake in the first place. Let's see here. We as a startup had only been around for a couple of months, and I think we had 4 engineers total at the time that we started using Snowflake. And so and one of the things that kind of sold us on it was we went on site and did a demo with them, and we loaded up all of our data, which in the solution we were using before, we had very carefully come up with the schema, and we'd really carefully tuned it to make like our key query work. And at Snowflake, they were like, we'll just load the data in real time, and then we'll query it, and you'll just see that it works. And it did without us having to do, we weren't choosing indexes. We weren't, there was really like no tuning at all. We just dumped all the data in, and we ran a couple of our key queries, and we were really impressed with the performance. So I would say it obviously depends on the size of your organization, but we never ended up having a database administrator for Snowflake. There just aren't that many knobs that you need to turn in order to make it work well. The only thing that we ended up doing tuning-wise was choosing the cluster keys for a couple of the tables, so that as they got bigger and as we had more things running in parallel on them, we were sure not to conflict. But that was about it. All right, I'm going to look for one more question, and then I think we'll be out of time. Here's a great question. The major considerations for planning around cost when using Snowpipe versus using the copy command to ingest data. So Snowpipe came out after we had already built our first versions of our ETL. And my first, it was a relatively straightforward thing to do. And so when Snowpipe first came out, I was kind of like, why would we convert to this new thing? We already have something that works. But Snowpipe will greatly reduce your bill because it uses a shared warehouse. And so it's using like 1/8 of a warehouse. And so that means that you can run your ingest way more often and pay less for it. So I would highly recommend checking out Snowpipe, even if you've already built some version of ETL, just if it means for reducing your bill. It is guaranteed to be cheaper than doing it yourself, because if you do it yourself, you have to do it on your own warehouse, which you can do things concurrently on your own warehouse. But if you don't have anything else to do, every 3 minutes, for example, then that means you're going to have a warehouse up all the time just to do your ingest, as opposed to using a partial warehouse, which is what Snowpipe allows you to do. All right. Thank you so much for all these great questions. I hope that you learned a bunch, and we'll be sending out a recording tomorrow, and also sending out some extra materials to answer some of these questions that came in.